All right, this video's Unit 10, Day 1, Area. So we've talked about this before, but there's a difference between net area and total area. Net area is what you're going to get when you take an integral. So this is going to be, the answer to this is going to be net area. And so net area would have all of the areas that above the x-axis would come out as a positive result. The areas, the physical areas that are below the x-axis would come out as a negative result. Your net area, so for example, is if this was b, the integral from 0 to b of this function would be the net area, the positive physical area and the negative physical area netted together. Total area would be, for example, if this is a, that I would integrate from 0 to a of this function, I would get a positive. If I integrated from a to b of this function, I would get a negative. And so to get the total area, I would have to somehow make those both physically positive. This is positive here. So I could subtract the negative area. I could add the absolute value of the negative area or something like that. But in other words, in order to get total, I actually have to break up the sections so that I can figure out the total area. Net area, the integral will take care of it for you itself. So for example, this is the graph of sine. So if I was going to do the integral from 0 to 2 pi of sine, well, I can see that I'm getting a positive area here, a negative area here. We know that this is a cyclical graph and is symmetric as far as its shape and size. So this really would be equal to 0, and you can check that by integrating on your calculator as well. And it makes sense because the positive area above would be netted out with the negative area that's below the x-axis. So if I wanted the total area, I'd have to break this up. I could do the integral from 0 to pi of sine x dx, and then the integral from pi to 2 pi of sine x dx. And just like I was talking about before, I could subtract it because I know I'm subtracting a negative, which would be to add it. I could add the absolute value of that, but somehow I have to sort of get the physical area to become positive as a result. So net area is the area that you find when you're calculating an integral. The area, any physical area below the x-axis is canceled out with any physical area that's above the x-axis. And total area, so that's the word you're looking for to tell you you're doing something different. Total area says take all the areas below and above and basically add them as if they're all positives. So here I'm being asked to find the total area of the region between the curve and the x-axis. So I'm going to sketch a graph of the function to start. And I know that this is a line. I'm down here, here, and at -1, 2. I have a point there as well. This is -4, -1. And my graph looks something like that. Okay? So I want to figure out what the physical area is. I have this area here, this area here. I can see that the integral, if I integrated in number 1, I would be getting a negative result. So for example, my integral for area -1 would be from -4 to -3 of this function. And I take its antiderivative, x squared over 2 plus 3x, and I'm going to evaluate it from -4 to -3. That is 9 halves minus 9, minus 16 halves minus 12. Make sure you have those parentheses so it will distribute. This comes out to be -1/2. Again, doesn't surprise me that my area would be negative below the x-axis. My area 2 is going to integrate from -3 to -1 of this function, x plus 3 dx. So again, I get the same antiderivative, but I'm going to be evaluating it from -3 to -1. This is 1/2 minus 3 minus, now I have to do my result when I plug in -3. 9 halves minus 9. Again, you can stop the video or pause it to check these numbers that you would be able to do them yourself as well. And this comes out to be +2. Of course, this might be one where using geometry is actually pretty easy because these are just triangles. So if I want my total area, I would basically be wanting to take my positive area and add the absolute value of the negative area, and that comes out to be 5 halves. The net area of this would be 2 minus 1/2, which is 3 halves. And you can check that that should be the same result you would get if you integrate this function from -4 to -1. Again, the antiderivative is the same, but where I'm integrating it from is different. This comes out to be 1/2 minus 3 minus 8 minus 12, and when you simplify that, you get 3/2, so you can check that that is equivalent. All right, find the total area of the curve. Again, total is what tells me that I'm having to like look at the different sections, see the ones that are above and below the x-axis. So I do need to know a little something about this graph. I know that I can factor out an x, because this is a polynomial. They all happen to have an x in front of it. And then this can actually be factored into x minus 2 and x minus 5. So why am I doing that? Because I can see that this graph is going to be broken up into different sections between 0 and 5, right? This would give me a 0 of x equals 0. This gives me a 0 of x equals 2. This gives me a 0 of x equals 5. That means that the graph is crossing the x-axis at those points. Those are the x-intercepts. So that means I have to look at the areas between those points separately. So, for example, I'm going to start by integrating from 0 to 2, this function here. And when I do, I get my antiderivative. And I'm going to integrate it from 0 to 2. When I do that, I'm going to get 4 minus 7/3 times 8 plus 20. And that reduces to be 16/3. Again, feel free to pause the video and check the numbers. So that tells me that the graph between 0 and 2 is above the x-axis. Now I'm going to integrate from 2 to 5 of this function. Again, the same antiderivative, but now I'm integrating it from 2 to 5. And when I do that, I'm going to get some messy numbers. Again, you can check with your calculator. This comes out to be -63/4. So that tells me that between x equals 2 and x equals 5, the graph goes below the x-axis. So my total area is going to be the area above the x-axis plus the absolute value of the area below the x-axis, which is coming out to be 253/12. And again, you can check that by graphing or by integrating on your calculator. So let's say I had this graph here. We'll call it f of x. This is 5, 3. Okay, this is f of x. So if I wanted to model the area between, if I did the integral from 0 to 5 of f of x dx, this would be the net area. If I wanted the total area, again, I have a couple of options of how to do it, but I would integrate from 0 to 3. That I can see is going to be positive, plus, and now I'm going to have to add the absolute value of the integral from 3 to 5 of this function. Okay. Again, total area, you have like a triangle, you have something up here. You would break it up into 2 different sections, depending on what crosses the x-axis, where it crosses the x-axis. Okay. So let's ask ourselves a question. When, if ever, is the total area underneath the curve of the function equal to the integral on that interval? Okay, so the only way that your total area and the value of the integral would be equal to each other is if the function, if f of x is all positive or all above the x-axis, right? Because that's the only way that those two would be equal to each other. Otherwise, the integral would have some netting out, something that's being subtracted from it, right? When, if ever, is your total area under the curve less than the value of the integral? And the answer is going to be never, right? They might be equal to each other, like we just said up above, if you create a positive function that's always above the x-axis, but the integral, the net area, will always be the same or less than, because it is only having things potentially subtracted from it as well. When, if ever, is the total area underneath the curve greater than the integral? Well, the total area will be greater if you have some function that goes below the x-axis, because this area here will contribute a negative result to the net area. And so in that case, your total area would be greater than your integral value. And let me just add one more page. This is just an interesting other example. if I have this function here, that's the beginning of cosine of x, and this is 1, so this is cosine of x, and I want the area of this shaded region here, then we can think about how we would do that. So this is just really manipulating with definite integrals. But the way you could do that, because remember, getting an integral is always going to get you the area below the curve. Well, first you could integrate from 0 to pi over 2 the function that's on top, which is this function here, which is really just 1 with respect to x. That's going to give you the whole blue. And now we want to subtract from it the white area here, which is the integral from 0 to pi over 2 of cosine of x dx. So we can use the fact that that integrals give us net area to help us manipulate and find more complicated areas as well.